is Professor Dr. Felipe Lopes. Eduardo Leite is a PhD candidate at this university, and you have about 50 minutes, so good luck.
Thanks, Professor Flávio. Good afternoon for all. My name is Eduardo, and I will present the work titled Traveling Wave-Based Fault Location Formulation for Hybrid Transmission Line with Two Sections. The co-author is Professor Felipe Lopes, who is also my PhD advisor. So, a brief introduction and motivational points about this study on fault location in hybrid transmission line. There are areas in which the use of overhead transmission line is restricted due to several factors, such as visual impact and physical limitations. The utilities have increasingly applied the combination of overhead transmission line and underground line, cable line, resulting in hybrid transmission lines. The fault location procedure is crucial to speed up the line restoration time and provide support for the auto-reclosing procedure that must be blocked in faults on the underground cable line section. So the mathematical development derives from the classical two-terminal traveling wave-based fault location. In the classical formulation, the line propagation velocity is considered uniform and constant along the line. But in hybrid transmission line, we have two sections with two different velocities. So this application is not appropriate for fault in this kind. Therefore, by the application of the classical method, considering faults in the section 1, this point, it's necessary to compensate the deviation error delta epsilon 1 here between the real and theoretical time, measured time. In order to compensate the deviation error for fault in section 1, by the properties of similar triangles, we can obtain the equation of the deviation error for faults in section 1. Substituting this equation in the classical fault location formulation and considering alpha as velocity ratio, the formulation for fault in section 1 is calculated in here. So similarly, for fault in section 2, we apply the classical method, fault location method, and it's necessary to calculate the deviation error delta epsilon 2. Illustrate here. Again, by the properties of similar triangles, we can obtain the deviation error for fault in section 2. And substituting this error in the classical formulation, we can obtain the second equation for fault location in section 2. Once D1 and D2 are calculated, the studied fault location problem is reduced to the detection of the faulted hybrid line sections. So using the fault location distance formulation for faults in section 1, it should be noted that D1 must be smaller or equal the line length of section 1. Solving for delta t, we have the first boundary condition, where tau 1 and tau 2 are the line propagation time of sections 1 and 2 respectively. And the second boundary condition derived from the equation for faults in section 2, where D2 must be greater or equal L1. Solved for delta t, we have the second boundary condition. So aiming to evaluate the studied method, 500 kV 60 Hertz hybrid transmission line was implemented in Alternative Transient Program, ATP. The section 1 of the hybrid transmission line were assumed to be an overhead transmission line, and the section 2 were assumed to be an underground cable line with 200 kilometers each. 18 fault cases were simulating ATP, where faults in range from 10% to 90% with step of 10% in each of the two sections. The measured delta t was used to calculate the fault distance in each case. So, analyzing the figure, the maximum error for the studied formulation is about 70 mirrors. In this figure, it is illustrated by this red mark. Attesting that the studied formulation is accurate for hybrid transmission line fault location application. On the other hand, applying the classical method using uniform velocity, VP1, propagation velocity of section 1, or average velocity between the section 1 and section 2, and the results completely diverse with errors about 200 kilometers. The use of the average velocity reduces the error, but does not provide accurate fault location. So finally, the conclusions, the use of an approximate and uniform velocity applied to the classical method is not enough to guarantee an accurate fault location in hybrid transmission line. The use of the average velocity provides some reduction, but does not provide an accurate fault distance estimation. And the student formulation has shown to be accurate, resulting in errors smaller than the typical tower span. So, thank you very much.
So, Eduardo, thank you very much for your presentation. Congratulations. And we have time to some questions. Do you have any question? I have a basic question because I couldn't see in your presentation. What kind of transmission line model and cable model have you considered?
Thanks, Professor Flavio, for the question. The model of the transmission line were considered factly transposed, and just the sequence parameters was modified by a reference in literature. So the model is the same for overhead and cable line, just the sequence parameters.
Was it constant or
constant? No, frequency constant.
Okay. And more question? So we have time. Another question, and did you? It's a suggestion. Okay, I think you could verify this methodology in both aerial and ground modes, and maybe combining the information.
So there is other study in course, I don't know, we are reading. So yes, we are analyzing the combination and the study of the models separately. Yes.
Okay. So, thank you very much.
Thank you, Professor.
The next presentation will be using current traveling wave to implement directional element in parallel lines. It was not updated. I would like to invite Fernando Marinho de Magalhães Jr. He is currently a master's degree here. Master?
No, pursuing master degree.
Okay, pursuing master degree here at this university. So, good luck.
Yeah, I'll be dating the presentation. My name is Fernando, and I'm pursuing master degree. My advisor is Professor Felipe. And this work Well, my research field is fault location in parallel lines, double circuits or parallel lines. For the time to submit this work, I didn't have the results, but this directional element, I needed to use this to implement the fault location method. But we see that it can use for another purpose. So the title of the work is Using Current Traveling Waves to Implement Directional Elements in Parallel Lines. It's not working. I'm confusing here. Okay. The first one, please. Forward, please. Okay, faster. The goals of the work is propose a new traveling wave-based directional element used on current signals for parallel lines. A method using voltage and current traveling waves has been proposed. The author's arguments are that the first voltage traveling wave can be accurately measured the time, not the amplitude, but it's enough. In the vision of the authors, it's enough to promote accurate direction of the fault. But as we know, the coupling capacitor voltage transformer does not accurately reproduce high frequency signals in its secondary winds. This is motivation of the work. If you have a double circuit parallel lines topology, we can use the current travel waves that comes from the both lines. The classification of the fault in forward or reverse can improve the performance of other protection schemes and accelerate the trip decision without compromising protection security. We could use it with phasers, but if you have ultra high speed protection, that's not enough time to correct estimate the phasor. Because of that, has been proposed directional elements using traveling waves. If you have a directional element, by using communication channels, and it not need to be synchronized, we can identify the fault as internal, classify the faults as internal or external of the lines. In case of the internal faults, the method can also identify the fault line. In case of the internal faults, if you have positive refraction coefficients, this can be demonstrated if you take the equation of refraction coefficient coefficients, and consider that you have another line connected. Well, if you have positive refraction coefficients, the measured current traveling waves will have different polarities in each terminal, indicate a forward fold for both terminals, in this case of internal fold. Then for bus M, the directional element identify a forward fold, and in bus N, the directional element would identify a forward fold too. Thereby, it is an internal fold. External folds. If you have positive refraction, again, if you have positive refraction coefficients, measured current traveling waves will have same polarities in terminal M, indicate a reverse fold. This happens because the wave arrives at bus and the refraction is seen at both current transformers of the parallel lines. But if you have in bus N, if the waves does not arrive at the same time, measured current traveling waves will have different polarities in terminal M. Likewise, traditional directional elements. Because in this case of external fold, for bus M, it will be reverse fold. For bus N, it will be a forward fold. The traditional directional elements will identify in this manner. But in this case, if both lines have the same propagation velocity and the same length, in a manner that both waves arrive at the same time at bus N, we have a wave interference, and a reverse fold would be identified, or no fold could be identified. In this case, it could not work well. And for implementation, we take it in account. I'll explain later. For the algorithm implementation, we consider on the first wave, because it carries the correct direction information. If you take subsequent waves, the refraction and reflection and refraction in the system buses can indicate incorrect directionality. The method always works adequately for internal folds. Internal folds, it will work well always. For external folds, in specific but common cases, the parallel lines, it's common to have the same lengths or double circuits, in the case specifically in double circuits. The method could indicate a reverse fold instead of a forward fold, or the fold could not be identified. Because of that, the proposed method can only be used to accelerate trip decision and cannot be used to block trip. In other words, if the method indicates a forward fold, it is a forward fold. But if it indicates a reverse, it could be a forward. But if you use the method to accelerate, it's advantage, because it always works. And because of that, the algorithm implementation only detects if the forward fold occurs, or not detect the forward fold, or not detecting a forward fold. And if you detect a forward fold in both terminals, it is an internal fold with certainty. The proposed algorithm was elaborated to detect forward folds and internal folds by using a communication channel. If you have a communication channel, we could identify internal folds. And it does not need to be synchronized, because if you have the information, it's a forward fold in one terminal, in the other terminal you have information that it's a forward fold, I need you to send this information. It does not need to have a timestamp for that. Obtaining the current travel waves. We use Clark's transformation Clark's transformation tool, reference to each phase, and use alpha and beta components because the aero mode have faster propagation velocity. Use a differentiator smooth filter applied in alpha and beta components. With that, we extract aero mode current traveling waves. Obtain the directionality. We make this product. The product is, we put a negative signal for choice. And the TWL is the product obtained. TWL1 is the aero mode component for one of the parallel lines, line 1, we call. TWL2 is the aero mode component for the other parallel line, line 2, we call. A positive threshold is applied in TWL. If it's exceeded, then a fold fault is detected. If a fold fault is obtained in both terminals, then an internal fault is detected. If an internal fault is detected, we make this comparison with the absolute values of TW1 and TW2. The greater, you indicate the fault line. Evaluation of the method. We use this system that's proposed by Power System Berlin Committee of I3E, which considers a coupled parallel line with transposition cycles. This figure is in the draft that is referenced in the paper. And this is the system in alternative transients programming with the transposition cycles here. And have a derivation too, synchronous machine also represented. We choose, for demonstration of the method, we choose an internal phase ground fault and an external downstream phase A ground fault. In the case of internal, we show here only the aero alpha component, reference to phase A, as it demonstrates the operation of the method. As you can see, the threshold is exceeded for both terminals, and as you can see here, the line 1 is the fault line, and the greater values indicate the fault line. That is line 1, as we expected. External downstream faults. In this case, we see that no fault was detected in the local terminal. That is the farthest from the fault. The fault is closest to the remote terminal. As you can see, the product is negative. The product calculated is negative, and the blue line that you cannot see here, but it does not. It's near 0 because of wave interference, but it does not indicate an internal fault. And important, we show that the method does not indicate a fold fault, a wrong forward fault. Results. The presented traveling wave-based directional element has shown a good performance in analyzing fault scenarios, being able to correctly indicate forward faults without the use of voltage signals. By using directional elements at both line ends, internal faults can also be correctly identified. In case of internal faults, the fault line can be identified by analysis of traveling waves amplitude. On my closing what I say in the first before the presentation, we use this method to identify the reflected waves in your fault location method. And as we cannot count with the first voltage travel wave, because the reflected wave, it will be a second wave, third wave, then to identify correctly the direction of reflected waves, we use this directional element. Okay, thank you.
Thank you very much for your presentation in this workshop. And do you have any question, please?
Congratulations for your presentation.
Thank you.
I have some comment and question. The communication channel, how you model in your problem in the saturation has some impact on the results.
The TC is saturation communication.
Communication.
No,
No, sorry. The saturation of the TC, CVT.
Current transformer.
Isso.
No, we didn't make a model of that. But I have an argument. Traveling wave occurs quickly. It occurs in. It's only time to the wave travel from fault to the terminals. There is not enough time to see saturation. For traveling wave, a point of a problem is the CCVT, because it does not have a frequency response, a good frequency response. Then we could not identify the voltage current traveling wave. Voltage traveling wave. We could not identify correctly, or not identify at all. For current travel waves, we do not have this problem because the current transformers have a good frequency response, and it produces the primary signals almost the same. Reproduce well the primary signals in its secondary windings. Current transformers have the problem of saturation, but it normally occurs one quarter of cycle after the fault, and it's the waves arrive before that. Then the problem of current transformers, it's not a problem generally for traveling wave methods.
Excuse me, I just want to present some brief clarification about everything Fernando has just talked about. In fact, we have to use some models to simulate communication channels, but we have already some functions which are working using dedicated fiber optic links, and in this case, when they are dedicated, the latency is almost deterministic. So if you want to simulate this kind of communication link, we just have to put a delay on the communication timestamps, so it's easy to perform. But in this case, we just use the signal separately from each line terminal, so we do not have to analyze timestamps, so the synchronization is not required. Regarding the current transformer saturation, I agree with Fernando. Although he shows the figures with some reflections over the time, this algorithm works based on only the first incident traveling waves at the monitored terminal. So you can detect the direction of the fault in the very first instance of the disturbance. So it's not a problem to, if the current transformer saturates, it will occur some milliseconds after. Just a brief clarification about that.
Hi. Does these parallel lines belongs to the same system? For example, for the same system of generation?
Yes, same.
Not the same voltage, but the maybe I want to know if these two parallel lines belong to the same system of phases, A, B, and C, R, S, T.
Well, is this the simulated system? It's a double circuit. And we have these transposition cycles. The system is a double circuit and the same voltage levels at the ends. A, B, C. Yes.
But how is the monitoring between the phase in the system in high impedance?
Sorry, I didn't.
How is made the monitoring in the lines?
Current transformers. Current transformers in each phase. Current transformers in each phase. We have measured currents. This transformation is applied for, well, 3 transformations, but there are 6 transformations because we have the transformation for line 1 and transformation for line 2. And we have alpha and beta components. Here is for line 1, alpha component is for line, it's for line 1, it's for line 2 component. In the remote terminal, here is the local terminal. Only alpha component, but we could put a beta component. It is a composition of the A, B, C currents.
I have just a question, very fast. And by using the traveling wave, we can get 3 types of information regarding the traveling wave. The time information, the magnitude information, and the direction information. So by using CCVT, did you evaluate the effect of CCVT in these 3 types of information in order to exclude the CCVT?
In this work, one for motivation that use the argument that a CVT does not have a good frequency response. In our work, we use only current transformers.
You didn't evaluate it yet? This
Fernando was not in the work where we evaluated this kind of problem. He's working now using current traveling waves, but we have already evaluated this problem when we use CCVTs to measure traveling waves, and we have problems to in measuring the amplitude of these traveling waves, but the polarity in the first incident traveling wave is not lost, so we can use that, and we have already some time domain relays which operate using these voltage traveling waves, but only the first voltage traveling waves. If you need the reflections, it does not work. So, but we have problems. It attenuates the voltage transients.
So if you combine this information, maybe you could get just a single measurement in future works. So we don't have more time.
This method have been proposed, as I said, is referenced in the paper that use which Professor Felipe talked about.
Okay.
Manufacturer has proposed that.
Because combining these two information, maybe you could reproduce your methodology by using just local information. Maybe I don't know.
Current and voltage, and it proposes using only current.
Okay. So thank you very much. The next work is shift parameter sensitivity on the computation of unstable reduced order model via truncated balanced method by yourself, Eco, and Professor Dr. Francisco Damasceno Freitas. So, good luck.
Greetings. Now begins the presentation of the paper Shift Parameter Sensitivity on the Computation of Unstable Reduced Order Model via Truncated Balanced Method. And the main objectives of this paper are the application of projections onto the extended Krylov subspace, EKS, in order reduction of large-scale small signal stability power system models, and also the study of the impact of shift parameter on the quality of model order reduction from systems with poles near zero or even unstable poles. Here, we are interested in power system models of high dimensions, linearized, and we are using a representation of state space or descriptor system that is very useful because of their sparsity. And the problem of model order reduction we address here, it's basically a problem. We start with a model with elevated order, very elevated order, and we have to determine a new model with substantially lower order. That is, we have a full order model, and through the process of model order reduction, we acquire a reduced order model. And also we can represent with this illustration. We have this full order model, and after reduction, we have something like this reduced order model. There are plenty more techniques, and we select the balanced truncation method. The main purpose of this method is to find some transformation matrix, and to do this, we have to solve two matrix algebraic Lyapunov equations, and there are many techniques that solve these equations, but we prefer those that deal with large-scale systems. These are the two matrix algebraic Lyapunov equations, one of controllability and the other observability. And we solve them using projections onto the EKS. which has this form for the controllability equation. We construct the matrix to project onto the EKS using a process based on our node method. It requires successive operations in the form of A times B or inverse of A times B for controllability, and also the orthogonalization of all the columns with respect to the other columns of the matrix. After the projection, those equations have much smaller dimensions and can be solved by traditional methods. Now, when we have unstable systems, we consider a shift parameter alpha that actually makes a displacement in the complex plane on the variable x in the Laplace transform, such that all poles are shifted to the left half plane. This shift is performed in the state matrix of the system, and after this, the shift, we reduce the system as it was stable. It was stable, and then we apply a reverse shift to retrieve the reduced or the model of the original unstable system. Now we present the results for a system that has 606 states and 6,529 algebraic variables. This system is unstable and has its rightmost pole with real part 0.00294. To better quantify the error, we define relative error index as this expression based on a frequency response. Now we have the first figure. We select 6 values for the shift alpha, and we tested frequency response, comparing the full order model response and the 6 reduced models. We can see that for higher values of the shift, the frequency response at higher frequencies dominates. While with smaller shifts, we have better results. So, and with this value of shift very near but not equal to the value of the real part of the rightmost pole, we have a curve that's almost coincident with the full order model curve. Also have the error, the frequency deviation. We can see that with the smallest value of shift, we can have a better distributed error among the frequencies. And because we only spend a few values of shift, if we want to, now we want to see for a larger set of values for the shift, we have figure 3, where we spend the value of shift from near the value of the real part of the rightmost pole to 1,000. We can see that the error, relative error index, it starts decreasing as we decrease the value of shift, giving a very good result in this region. But we cannot use exactly the value for the shift, the exact value of the real part of the rightmost pole. As we can see, we have a very high error. That's because in doing so, we are allocating poles on the imaginary axis. We have a singularity there, and that makes an ability to reduce the model. And to conclude, we have studied the impact of this parameter shift. This strategy is appropriate to reduce unstable systems. And we have seen that this shift is not only necessary for the reduction, but an appropriate value of this parameter is essential for good quality model order reduction. And now the presentation has ended.
Thank you for your presentation. And sorry, I forgot to introduce you at the beginning. Yourself is a PhD student, and his advisor is Professor Damascene. I'm sorry about that. And do you have any question?
I've seen in your presentation that there was a pole that was really close to zero. That was the only unstable or nearly unstable pole in the whole thing, or there were several poles that you shifted all to the right side of the plane?
For this system presented, that was the only unstable pole. But there are also a few poles in the neighborhood of zero, but they are actually with residue zero. They are not reachable or controlled. We cannot control this poles, so they are not even considered in this perspective. We consider only this unstable pole located at with real part 0.00294.
So for the current moment, the model works for only a specific point that you can shift to the pole. There is not like several points that with the same parameter you can shift them all to the correct side of the plane and make the system stable, right?
If you have multiple poles, unstable poles, the strategy proposed here is to use the rightmost pole, the real part of the rightmost pole, so you can stabilize the system, because the shift is applied equally to all the poles, shifting all the. It's basically a displacement of the complex plane on the.
You just shifted the axis, right?
The real axis you shift to the left.
Oh, okay. Thank you.
No more questions? So, thank you very much. Now, we have another paper on compensated synchronization errors in two-terminal-based fault location approach. The presenter is Jessica. Jessica is a master student here at this university, and her advisor is Felipe Lopes, Professor Felipe Lopes. So, good luck.
Thank you. Good afternoon, everyone. I would like to thank you all for being here. Me and the PhD Professor Felipe Lopes are working a study of the fault location techniques available on literature. You want to compare them among themselves and show its weakness and the highlights in the. Sorry. Okay. Our paper for this workshop is on compensated synchronization errors in two-terminal-based fault location approach. We all know that power systems grids are expanding rapidly in order to attend the need of continuous and reliable energy supply. We also cannot see that in the recent decades, induced by the regulation and competitiveness of the sector, there has been a growing investment to minimize the restoration time after line faults. So the subject fault location have been received large research efforts. So there's a lot of ways to categorize the fault location techniques. I am present this categorized methods. So we have two big groups, the knowledge-based methods and the transient-based methods. The knowledge-based methods, we can see the impedance-based algorithm, the artificial intelligence algorithm, and in transient-based methods, you have the high-frequency methods, we have the traveling wave methods, and also the artificial intelligence methods. In this work, we are going to study an impedance-based method. Among the impedance-based fault locators, we can see two terminal-based methods and one terminal methods. These ones that use data from both line ends are commonly reported as the most reliable. These methods are not affected by fault resistance or homogeneity of the system, but they require synchronization. Although most growing research are looking for methods that doesn't need synchronization data. We can use GPS to do the synchronization, but in case of the loss of the signal, the fault location procedure may be compromised. So this paper represents an application of an algorithm able to determine the synchronization angle to be taken into account in a method that would synchronize data. So this is the system that we're going to use to evaluate the algorithm. It's a 500 kilovolt system, and this is the Thevenin equivalent circuit, and the bus S and bus R. The algorithm that we use in this work is one of the most accurate techniques, and it considers the distributed parameters of the line and the line shunt capacitance. This is the paper, is written by John and Jamal to find the fault location distance. He takes account if part of the system and mesurates the voltage phasor of the fault. And this is the distance of the fault in PU, and gamma is the line propagation, and ZS, the line impedance, the impedance characteristics of the line. And the algorithm to determine the synchronization error, it independent of the transient characteristics of the analyzed fault records. It's based on the fault of the voltage phasors and the per-fault current, and depends on the accuracy of line transmission parameters. This is the paper. It's written by Belinda Cruz. And the synchronization angle is given by this equation. I will not present the maths, you can see in the paper. So, to evaluate the algorithm, we're going to use the distance presented by John and Jamal, and we're going to multiply all the phasors from the bus S by the operator synchronization. This is exponential here. So we use the analysis transient program to do the estimation of the fault at 0.25, 0.5, and 0.75 PU. And you can see here that with the synchronization, we can estimate a good fault is 0.01 PU difference error. And without synchronization, the algorithm didn't work. Didn't converge to a value between 0 and 1 PU. So we can conclude that application of the synchronization operator allows to use the algorithms originally developed for synchronization systems, and the estimate of theta depends on the system parameters, what may compromise the fault location performance if uncertainties inline parameters are relevant.
Thank you very much, Jessica. And now, do you have any question, please?
Congratulations, Jessica. It's an interesting work. How you intend to continue this work with your advisor?
We pretend to take a lot of methods, the most methods we can, and categorize all of them and compare them and say this one's good for this situation, this one's good for these systems. We also do a method, another paper, taking about evaluation of C, of the load angle, and the resistance of fault, and we want to do this with the methods with impedance base and maybe the wave traveling methods.
Thank you. Do you have another question? Other questions? So we have 50 minutes. When you state synchronization error, do you mean the case that there is no synchronization?
Yeah, in case of loss of the signal of GPS, there is a synchronization error between the two terminals or three, and we can calculate the synchronization operator. To do this on this work, with all the signals from ATP are originally synchronized. So we multiply all the phases from bus S by a delay of 18 degrees. And then we use the program to measure this error.
Okay. So, when the synchronization method, a GPS for instance, is worked normally, there is a small deviation of time in both terminals. Do you know about the impact of this minimal error time synchronization do you intend to evaluate this situation?
We don't have problem at this work because we are going to use offline estimating method. But I think it's a problem if you need to do this in real time.
Okay, but even in simulation, you could insert a little time deviation in each bus, and in this case, it's a minimal synchronization error, but maybe you could evaluate it because this could impact the traveling wave-based location methods.
I think you can do this.
It's a suggestion. And, no more question. We have 10 minutes. Okay. Okay, congratulations.
Thank you.
So the next paper is CCVT impact on the TD21 function security. Now presented by Professor Philippe Lopes. Professor Philippe Lopes is a professor, adjunct professor at this Department of Electrical Engineering at this university. So good luck, and you have 10 minutes extra in your presentation.
Thank you very much. Just waiting for the presentation. Okay. Good afternoon. Thank you, Professor Flavio, for introduction. This paper is part of a major research of this master student called Edson Custodio. Unfortunately, he was not able to be here today, and I am here to present by him. We counted with the support of our master student, João Paulo. Thanks, João, for all your support. And we are trying to understand some new functions, some new protection functions which are applied in time domain. Traditional phasor-based relays have been used for years, but now we are facing a new trend in the market in which the relays are not using anymore only phasors. They are applying some techniques that depends only the analysis in time domain, using instantaneous values, voltage and current instantaneous values. So in this paper we are presenting some brief explanation and investigation about the CCVT impact on the distance protection applied in time domain, which is called TD21 function. So let's try to present something about that. Well, in the recent decades, we are facing a growing demand for electric energy, and as a result, transmission lines are operating closer to their stability margins. It has been a cause for concern for all utilities because we may have problems when we may have problems when severe short circuits take place. So if you have little stability margin, so you can lose your stability. In this case, the protection operation times are very important. They are of utmost importance because they have to be considered when you are defining the amount of power to be transmitted through transmission lines. And just to illustrate this problem, I am presenting two very, very simplified figures in which we use the areas criterion to analyze the stability of a very simple system. So let's assume that I have a power system operating at this point where mechanical power is equal to the electrical power. So if I have a severe short circuit in such a way that the electric power goes to zero, we have the load angle increasing, and then when the protection operates, assuming that the system will come back to its original point of operation, we have this point going up right there. And then in this case, we have an electrical power greater than the mechanical power, so the machines will slow down, and so this system is stable in this case. In this case, we have to define this point of operation based on this time to operate of these protection functions. But since we are needing to transmit more and more power over the transmission lines, we wanted to speed up this protection. So if we speed up these protection functions, we have the chance to increase this electric power transmitted in transmission lines. So if I have the same severe short circuit, but my protection operates faster than the phasor-based one, so I have an unstable system, so I will not have problems in the case. And in this situation, in this scenario, the time domain protection function have shown to be very promising. In this paper, we, as I said previously, We are analyzing the distance protection applied in time domain, which is called here TD21. Let's talk a little bit about the traditional function, distance protection function, and the time domain distance protection function. It's well known that the traditional distance protection function is based on the impedance measured between the relay and the fault point. To do so, we usually use phasors, voltage phasors, current phasors, so we have to use current transformers and coupling capacitor voltage transformers if your system is a high voltage system. In time domain distance protection, we have some little differences because we do not operate based on phasor information, but we use instantaneous values to operate. So we analyze the voltage, the estimated voltage at the fault point, at the reaching point of this protection, computed using incremental quantities and the pre-fault quantities. These incremental quantities are the main goal of these incremental quantities is to analyze the pure fault circuit. So we compare the pure fault circuit voltage against the pre-fault voltage circuit. Okay. But in this case, we have to use also the current transformers and coupling capacitor voltage transformers because we need some measurements taken from these equipments, voltage and current measurements. Just to illustrate the main principles of the TD21 function, let's assume that incremental quantities are computed using this formula here, where ST is the actual instant sample. So we take the difference between the sample and the P cycles delayed samples. In this paper, we considered P equal to 2 cycles. So this function is valid only during these 2 cycles. After that, the phasor-based functions must be used because the incremental quantities are not anymore valid. So by using voltage and current incremental quantities, we can compute an operating and a restraining voltage. The operating voltage is based on the pure fault circuit, and the restraining voltage is based on the pre-fault circuit. And as a result, we have something like that. If we assume a fault in a transmission line LR, where my reaching point is at M0, if the fault is within the protected zone, we have something like that. The voltage profile using incremental quantities will be higher at the fault point, which represents the voltage sag at the fault point. And this voltage decrease until the line terminals. And since we are using incremental quantities, we are assuming that the load effect is eliminated or almost completely eliminated. So we can approximate the restraining voltage at the whole line as the pre-fault voltage. So since we are using only one terminal measurement, we can estimate this voltage, but we are not able to estimate what is happening beyond the fault. We have a linear equation so that the operating voltage tends to be greater than the restraining voltage for internal faults internal within the protected zone. But when the fault is outside the protected zone, when we apply the same methodology, we would obtain some operating voltage smaller than this restraining voltage. So we can distinguish faults from internal and external faults within this protected zone. Well, for the sake of security, the TD21 use some additional security conditions. We take this pre-fault voltage and analyze some delayed samples and compare it, use a minimal restraining level to obtain a final restraining signal, which will be used, which will be compared with the operating signal. So we take these 2 signals here, We compute the difference between these two signals, and if some security conditions are met, an integrator runs, integrating the signal, and if this integrated signal is greater than a security margin, we have the operation of this TD21 if whenever the overcurrent supervision indicates that a fault, the current level is higher than a threshold. In this work, the TD21 was implemented and set, such as reported by the developers of this function, and in this case, the Schweitzer Engineering Laboratories. Well, why we have to understand the impact of the CCVT on this function? Even when we are using phasor-based techniques, the CCVT transient response may affect the traditional phasor-based techniques, phasor-based protection functions. But now, in this recent trend in time domain protection functions, this effect may be even more, maybe cause for concern for us, because we can attenuate some transients, we can put to the signal some phase displacements. So we have to analyze if this function is secure, if this function will operate when it has to operate, or if it will restrain when it has to restrain. Analyzing a typical circuit, a CCVT circuit, we find a capacitor divider, a compensating reactor, which is used to compensate some phase displacements between primary and secondary voltage signals. We have the step-down transformer, which is responsible for adjusting the voltage level from the primary to the secondary windings. And we have a ferro resonance suppression circuit, which is also typically used in CCVTs. So we can imagine that the secondary voltage will not be the same. It will not be a replica of the primary voltage, because we have a lot of capacitors, we have a lot of inductors, so it's kind of a big filter, and we have frequency response associated to it. For frequencies other than the fundamental one, this secondary is not the same of those voltages found in the primary windings. So due to that, we have two problems. We have the transient response and we have the frequency response. These two problems are a little bit different and may apply some different problems on our function. So to illustrate this problem, the ADP frequency scan was used to estimate the frequency response of 3 CCVT models found in the open literature. All these CCVT models have a rated voltage of 230 kV and operating at 6 Hertz. And as we can see in this figure, we have only the expected response at the fundamental frequency of the system, in this case 6 Hertz. We have to understand the expected operation of this equipment as 1 pu of magnitude and 0 degrees of phase angle, because we have to have a unit gain without phase displacements. So if in my signal some transient component show up, they will not be properly represented in our secondary signal, secondary winding, sorry. To illustrate the transient response, we simulated fault with the inception angle at 0 degrees, just to show you that while the primary voltage stays in 0, the secondary voltage oscillates due to the energy stored in capacitors and inductors. So we have a problem, and our question is, does the CCVT affect the TD21 security? To test this problem, we simulated using the alternative transients program as a very simple system. We took a transmission line with adjacent lines, which were modeled using actual parameters. These lines are the adjacent lines are 100 kilometers long, and the protected line is the LT1, which is 200 kilometers long, and some AG folds were simulated considering different inception angles. Among the case studies, in all simulations, both primary and secondary voltage signals were taken into account during the application of the TD21 function, and the reaching of this protection function was adjusted 70% of the protected line, and faults external to the protected zone but very close to its reaching were simulated just to evaluate if the TD21 would have problem when the CCVT was used in each case. So about the obtained results, preliminary results in this case, the TD21 function showed to overreach due to the CCVT transient response. Among those three CCVT models, the CCVT1 presented the worst results since it was sensitized for faults up 77% of the protected line, even using a reaching point at 70%. Just to illustrate the cause of this problem, here we have the voltage, primary and secondary voltage. It's clear that there is a difference here between both signals, and when we compute the incremental voltage, we have a difference at this first part of the signal, but it does not result in a misoperation of this function. But in the secondary part of this signal, we have a problem because the V secondary is greater than the V primary, so we operate improperly. And how the operating signal and the restraining signal will behave in this case? Let's see that. Well, using primary voltage for this same case, we have this comparison, so we will operate only when the operating signal is greater than the restraining one. In this case, the integrator would operate, but in this case, it does not run, so we do not integrate. And the integrated torque does not exceed the security margin, so this function does not operate when we use primary voltage for a fault at 71%. On the other hand, when we use secondary voltage for the same case, we can see that at the first stage of the signal, the operating voltage does not exceed the restraining one, but within the second stage here, the operating voltage exceeds the restraining voltage, so the integrator runs, and then since the integrated signal exceeds the threshold, the TD1 operates. So as a conclusion of this paper, of this part of this research, we can state that the CCVTs may affect the security of the TD21 protection function, but it depends on the transient frequency response of the CCVT. We had problems for this model, but for other models, it may not occur. The TD21 developers suggest a reaching point slightly smaller than those used by traditional distance protection, so we believe that we will have not problem in practical, in real life, in real world fault case. And finally, we saw that the CCVT influence may be understood by analyzing the incremental voltage, and we are trying to perform some additional studies on solutions and on ways to determine the proper settings to be used in order to overcome such kind of a problem. But we really believe that this function is very, very promising. Thank you very much for your attention.
So congratulations for your presentation.
Thank you.
And do you have any questions to the Professor Felipe?
Congratulations, Professor Felipe.
Thank you.
Presentation, nice presentation. I think that signal process has key importance in these works that you and your team are presenting. Other topic inside this processing design is filtering. I think the filtering process in this study is well important to improve the quality of the work. I think this interesting problem to evaluate. Just a comment.
Okay. Yeah, I agree. I completely agree with you, Professor Damasceno. João Paulo has a lot to say about filters in this kind of function. We have faced some problems with the filters used in this time domain relay, which we are trying to model here in our lab. And yeah, if you change the filter characteristics, so we may have different outputs of this relay. But we are trying, there are already some papers in the literature that try to compensate the CCVT influence by estimating the inverse transfer function of this equipment, so you can eliminate this influence. Our colleague here, Romulo, has worked with this kind of filter yet already, so we are counting with his support for future works. But I agree completely with your comment.
Okay, any more questions? Felipe's students, now it's time to... No question? I have a question, Felipe. Could you return a few slides, please, in the frequency response of the CCVT, please? Yes. I could see that the fundamental frequency, you have a unitary gain, the magnitude, for instance, but maybe few harmonics, maybe this CCVT, you have few harmonics too in a gain near 1. And my question is regarding the differential, not differential, the differentiation.
Incremental quantities.
Incremental, sorry. Regarding the incremental, you take the current sampling and you consider the sample 2 cycles before. It's a kind of filter, maybe, because the fundamental frequency is eliminated in the steady state. But if you have harmonic components, some of harmonic cannot be eliminated in this case. Did you evaluate this case?
Yeah, we have a wide variety of fault case simulated in our lab. In fact, the presence of harmonics may jeopardize the operation of this function. That's why this kind of relay use a lot of auxiliary filters with different cutoff frequencies. So we have no space and time to present all of this implementation here, but this implementation have a lot of other details which were not presented here, but we can clarify in another moment.
Okay, thank you very much.
Welcome.
So it was the last presentation. In few minutes we have the event, the end of the event. So thank you very much for your attention, and it was a pleasure to be the chair of this section.
Thank you.